Alright, so welcome back to particle physics and the Standard Model. This is lecture 16, and as you can see here, last time we wrapped up with the concept of isospin, which is just like spin but acting on nucleon states, meson states and so on, and just like you had spin multiplets, you have isospin multiplets, and all the algebra of spin goes through here, right, including the internal symmetry group on which these states act on, right. So, and then we ended with the Gell-Mann-Nishijima formula that related the electric charge with the third component of the isospin and the baryon number and strangeness, and we saw that this is in fact how you could assign the I3 quantum number given the charge, the electric charge, correct. Okay, so we will see further aspects of isospin here and work out some of the interesting consequences. One thing you can see from this formula, from the Gell-Mann-Nishijima formula, right, is that in the strong interaction, not just in the strong interaction, right, in any sort of interaction where I3 and the baryon number and strangeness are conserved, I am sorry, let me put it this way. So, where the charge and the baryon number and strangeness are conserved, this would imply that I3 is also conserved, just like you expect spin to be conserved, right. So, this is the way in which you would see that I3 is also conserved, okay. And of course, this happens for the strong interactions, this also happens for the electromagnetic interactions, correct. This may be so, however, this does not mean that, does not imply that the total isospin is conserved, right. Correct, that is not what this formula says, the total isospin could be whatever. So, let us illustrate that with a very simple process that we have seen again and again, pion decay, okay. So, what is the total isospin of the neutral pion? Not the neutral pion, what is the total isospin of the pion, what kind of multiplet does it live in? It is an isospin triplet, right. So, on the left hand side I have total I equals 1, and what is isospin for a photon? It is 0, right. We only talk about isospin for mesons and baryons, correct, and this is an electromagnetic process, right. So, you do expect things like strangeness and baryon number and electric charge to be conserved, nonetheless you see that the total I is not conserved, right. Of course, in the same breath I3 is, correct, because the I3 for the pion, neutral pion in particular is 0, we just saw that, right, in the at the end of the last class. So, and of course, since you can't talk about isospin for photons on the right hand side also, this is 0, okay. Let us look at another process. Let us take the lambda baryon, right, which I said is a UDS, correct, and let us take the decay of the lambda baryon to this channel, a pion and a proton, okay. Now, something is slightly off here, right. If I look at what the I3 of the left hand side is, that is 0 because the lambda baryon is an isospin singlet completely, we just saw that also, right, here it is. So, obviously the third component of isospin is also 0, but then what is the I3 on the right hand side, what is the I3 of proton? It is a half, right. and what is the I3 of a pi minus? That is -1, correct. This is in a doublet and that is in a triplet, right. So, the total I3 is -12. So, it looks like I3 is not conserved. Why could that be? Well, simply because this is not a process in which strangeness is conserved necessarily. Explicitly it is gone, right. You had a strange quark on the left hand side, it is gone on the right hand side, and that again is because which interactions violate strangeness? It is the weak interactions, right. So, in weak interactions S is not conserved. So, that implies I3 is also not conserved as per the Gell-Mann-Nishijima formula. Agreed? Baryon number is obviously conserved, total electric charge is conserved, but there is now an interchange between I3 and S, the strangeness, right. Notice that the formula still holds, okay, the formula does not is not violated or anything, it is just that I3 and S separately are not conserved in weak interactions, okay, and so on and so forth. Okay, good. Now, here is an observation in nature that to my knowledge can only be understood after you know what isospin is, okay, and that is the following. So, you must have heard of the Deuteron, correct? You obviously have heard of the Deuteron. So, what is a Deuteron? One way to say it is that it is an isotope of hydrogen, right, and this isotope contains an extra neutron basically, correct. And another way to say it is that it is nothing but a simple neutron proton bound state, correct, which is a Deuteron. Yes. So, it then we can then ask, the neutron and proton are part of an isospin doublet, correct. They are so similar in so many respects, correct. If you can form a neutron proton bound state so easily, Deuteron is very abundant in the universe, right, abundant enough to be detectable, right. Then what about a proton proton bound state? Let me call it a diproton. What about a neutron neutron bound state? Why did we never learn this in school? Why do we talk about Deuteron? Why does nobody talk about a dineutron or a diproton? Okay. That is because these bound states actually do not exist. And we can ask why, okay. And the only way to understand this is through isospin, okay. So, isospin is not just a cute concept that Heisenberg came up with, it has real consequences. This is what I mean by using symmetries as powerful tools to work out consequences in phenomenology, alright. So, let us see how. So, again recall that I can write the proton in isospin space as a 1 0 and a neutron as 0 1, correct. So, using your intuition from spin, if I were to form an isospin singlet using these two states, right, just like in spin I had an up state and a down state, right. So, this is in spin. Using your intuition from spin, what combination of these would form an isospin singlet? For spin, what was that? If you remember, for spin it was a combination that looked like this, right, an antisymmetric combination where I had up down minus down up suitably normalized, correct. this is in spin, correct. So, similarly I can write an isospin singlet in this fashion, correct, a proton neutron minus a neutron proton in isospin space, right, only in isospin space, agreed, and that is suitably normalized. So, now you can answer the following question: which combination would form an isospin triplet then? So, if I combine two spin half states, I can get a singlet and a triplet, right. Obviously the triplet is going to be a symmetric combination, right, one is an antisymmetric, the other is a symmetric combination. If I denote this with a 0, 0 to denote that it is an isospin singlet, then I can use this combination PP, we will call that 1, 1 in the triplet, and then I can also have NN that I am going to call 1 minus 1 in the triplet, and of course there is a another manifestly symmetric combination with Pn and Np, but with a plus now, right, with the normalization factor, and that of course is 1, 0. Good. So, these are the isospin singlets and triplets, right. So, how does this tell you whether there is why there is no PP and NN bound states? Now, for that we need to go back and understand what a bound state is, right. A bound state is one where the total potential energy of the state is negative, correct. In other words, you need to put in some amount of energy to isolate the constituents of the bound state all the way to infinity. What is that energy called? It is the binding energy, right. So, you need to put in the binding energy. So, I need the total potential or potential energy to be negative, correct. So, we need some information about the potential energy. This of course I do not expect you to know already, but it can be looked up, and nuclear physicists have worked this out. It turns out that the nuclear potential, okay, involving nucleons contains a term. So, I am going to write it like this, okay, which looks like this. So, a term with two nucleons basically, a potential term involving two nucleons would look like this. There is an S1 dot R, S2 dot R. To understand what even a bound state is, right, we have to go back and remember that, right. So, what is a bound state? It is one for which the total potential energy is negative, correct. That is one way to characterize a bound state, correct. Why is that? Because you need to put in energy to isolate the constituents of the bound state all the way to infinity, correct. And what is that energy called? That is the binding energy, right. So, you need to put in binding energy into a bound state obviously to separate it, right. Okay. So, that means we need to inspect first what the potential of these bound states looks like, right. And nuclear physicists have worked this out, and we know now that when two nucleons are involved, right. So, let me just say two nucleons, there is one particular term, an important term. So, I am going to write it this way, that looks like this. So, it is the spin of the first nucleon dot r and the spin of the second nucleon dot r, where r is the radial coordinate, right, obviously, but more important for us is there is a minus, and that minus is very important, okay, 3 times S1 dot S2. Okay. So, what does this tell you? If you did not care about the first term, right, from the second term what can you say about the existence of a bound state? This tells us that you want S1 and S2 to be aligned as opposed to anti-aligned, right. If they are aligned, then the second term is negative, correct, and that would imply a bound state. That is one necessary condition, correct. If not a sufficient condition, definitely it is a necessary condition, agreed. There is a minus S1 dot S2 term. So, let us see which of these combinations, okay, these combinations, which of these would give us aligned spin states and anti-aligned spin states. Okay. We worked out the isospin. What about the spin? That is important to consider. Why? Because Pauli's exclusion tells us that you have to consider the antisymmetry property of exchange of fermions for all wave functions, right, or in other words I can write schematically the total wave function as 3 components: exchange in literal spatial position, so let me call it psi 1, and then exchange in spin space, and now in this case importantly exchange in isospin space as well, correct. Okay. So, now let us look at this, okay. In particular, so this is trivial, right, this is just this is always a given. That means we now have to make sure that this combination, the spin and the isospin combination is antisymmetric, right, because these are after all fermions, correct. In other words, if I have the spins, okay, so let me call this spin. So, spin, if I have the spins aligned, then I better make sure that the isospin is in a sense anti-aligned, or said differently, I mean not in a sense, literally anti-aligned. So, said differently, I have to make sure that the isospin is in a singlet state, right, because only the singlet state lets them be anti-aligned. Only in the singlet state you have Pn and Np. In a triplet state you have both Pp, Nn, that is you have both aligned isospins and anti-aligned isospins, but in a singlet state you have only anti-aligned, correct. So, if I want the spins to be aligned, let me now put a column for isospin. For isospins, I need to pick the antisymmetric combination. Do you agree? And similarly, if the spins, so the N here stands for nucleon, okay, either neutron or proton. So, N is either neutron or proton, and if the spins are anti-aligned, then that means necessarily that would pick in isospin space the symmetric combination, either +1 or 0 or -1. So, if it's got it right. So, if it's antisymmetric here, it is symmetric there and vice versa. Okay. Now, you should be able to answer why can't proton proton and neutron neutron form a bound state? Because they live in the symmetric combination in isospin space, correct. The 1 1 corresponds to proton proton proton, and the 1 minus 1 corresponds to neutron neutron, and that necessarily means their actual spins are anti-aligned, and if they are anti-aligned, then in the nuclear potential they contribute a positive term and you are not going to get a bound state. Good, clear? No bound state. Okay, very good. So, that ultimately ends our discussion across all these lectures on the various quantum mechanical aspects of this course and all the symmetries other than Lorentz symmetry and gauge symmetry. Okay. So, we saw a few global symmetries here, we saw discrete symmetries both in space time P and T and internal symmetries like charge conjugation, and we saw how symmetries showed up in spin space and isospin space and so on. So, we have a lot of building material now to go on and construct the standard model itself using the language of quantum field theory. Okay. So, the texture of this course is going to change from this point. We are going to be talking a lot in terms of field theories. I will work through all of it from scratch and it is going to become very QFT heavy, and we are going to see exactly what the standard model is, and in that process we will answer a lot of questions that we raised earlier. So, we saw for instance that parity is maximally violated, but I did not tell you why exactly. The from the standard model we will begin to understand why that could be so, and we saw that I also said that CP violation in the weak sector is possible if you have at least 3 generations. Why is that? We will see that. Okay, and then we talked about the strong CP problem, that we expect to have large CP violation, but then we do not see any CP violation. So, why do we expect to have large CP violation? Again, when we construct the standard model we will see that. Okay. So, quantum field theory is all about putting gauge symmetries together with Lorentz symmetry. Okay, and there is a systematic way to do it, and from this one expression of quantum field theory turns out to be the standard model. Okay, so, that is the broad spiel of where we are going. Let me first write down how we are going to construct the standard model. So, do not worry if you do not understand these words much, we will catch up on all of this. Alright. So, I am just going to give you a brief outline of where the course is going to go in the next 10 to 20 lectures or so. Alright. So, constructing the standard model. Okay. What are we going to do? The first thing we are going to do is, so I am going to write that as 0. The 0th step is understanding what we mean by quantum field theory. Okay. This would be how we put together special relativity and quantum mechanics. Okay. And we will do this with a few examples. In particular, we will do this with a spin 0 field which will involve an equation that I am sure you already have heard of or used, the Klein-Gordon equation. Okay. Once we do that, we will construct the theory of quantum electrodynamics, okay. And this will turn out to be a very important sub module, because if you understand quantum electrodynamics, you will understand a lot about the standard model. So, I like to call this a toy standard model. Okay. So, what this will involve is to put together a quantum field theory involving Lorentz invariance, that is special relativity, right. But I am not going to write quantum mechanics because the word quantum is already there in QED, and this we will see in the setting of one particular symmetry, a unitary group that we call U1 because it is dimension 1. I am giving the label EM because that is what gives rise to electromagnetism. But the new word here is gauge symmetry, okay. And I am going to put the word symmetry also in quotes because there is a lot of debate about whether a gauge symmetry is really a symmetry or just a redundancy in field descriptions and so on. Okay. So, once we master that, we will go on to the actual standard model, and this I am just going to call it QED writ large. That is, we will use all the concepts of QED, but in a slightly non-trivial way. We will see how to expand this and generalize this and so on, okay. So, this will now involve putting together Lorentz invariance, that is always there. Without Lorentz invariance, none of this is going to work out, okay. We are always going to assume Lorentz invariance, plus more gauge symmetries, including non-abelian ones. What are non-abelian groups? We saw, right, those in which commutativity is not a property, correct. The elements need not commute with each other. It is really, you do not have to have it as a in part of the definition of a group, correct. So, what are the non-abelian ones in the standard model? We will have an SU3 and I am going to label it with C for color because that is what describes quantum chromodynamics, okay. And you will see that we will have an SU2. This is different from all the SU2s that we saw. This is an SU2 that acts on states that are charged under the weak force. So, we call that a W, and then we will see there is a special abelian group called hypercharge denoted with a Y, and that this constitutes, these two together constitute the electroweak force, okay. And we will see how this combination breaks down to QED basically. Once we construct the standard model this way, we can start deconstructing it and see how to get back QED. This is the combination where you lose some of the symmetry. This literally happened in nature, and then you ended up with a smaller symmetry that describes electromagnetism. So, what do we mean by losing symmetry? The technical term is symmetry breaking. Okay, we will see how to do symmetry breaking, in particular via the Higgs mechanism. Okay. So, this is where we are going, all right. So, let me close by quickly explaining what I mean by this new word gauge symmetries. So, we saw that there are continuous symmetries, correct. What are some continuous symmetries? Rotation, right, and spin, isospin, all these things involving SU2, SU3 and so on, correct. Of course, Lorentz invariance is also a continuous symmetry, correct. Now, some of these were internal symmetries, right, that is they did not involve space time. For instance, all of the isospin discussion involved internal symmetries. There were some internal quantum numbers you wrote the neutron and the proton as a quantum superposition such that all the rotations were in some sense did not involve space time, they were internal to the proton and the neutron, correct, and these happened on some abstract isospin space. So, these are basically internal symmetries. Now, if the internal symmetry, to take a simple example, if the internal symmetry involved say a phase change like this, okay, if a theory is invariant under a phase change like this, all right. So, what is the Noether charge of this? This would be some charge, correct, some global charge. This is how we get baryon number and lepton number. Now, I just said the word, in this case this would be a global symmetry, okay. But suppose even though it is an internal symmetry, right, suppose that phase actually depended on space time coordinates. That is, even though it is an internal symmetry in the quantum state, even though it is a, there is a transformation in the quantum state, the amount of transformation, if that depends on the space time label, right, if that varies from point to point in space and time, then would not you call that a local symmetry, correct. These local transformations would now constitute a gauge. This is what we mean by a gauge symmetry. So, people use local and gauge interchangeably, all right. So, that is what I am going to do too. Now, you might ask why do we want to call this a gauge? We talk about meter gauge and broad gauge and all that, right. That is literally the sense in which it was used the first time. This word was used by Hermann Weyl, the mathematician. He used it for a scale invariant theory. What is scale invariant theory? If you zoom in or zoom out, the theory does not change, okay. Whatever resolution you use to work the theory out in, the theory does not change. So, since he historically used this for a scale invariant theory, he used this word gauge to denote the size of the components of the theory that he was looking at, okay. So, he was using the word gauge in the sense of size, but then the word stuck for other theories as well, although it makes no sense. So, we are just stuck with it, okay. So, I will end there, and then in the next lecture we will see how to build any quantum field theory, and we will see how to put together relativity and quantum mechanics in a sensible way, all right. Okay, I will end there. Thank you. See you next time.